Um, Good evening, everyone. Hello, good evening.
Good evening.
Good evening.
Okay, apologies for the delay. I'm very, very, very sorry. I'm very sorry. I think something just caught me up and I had to just run like and then get home as soon as I can. So this how soon I could get home. So apologies for that. So please let's start the session in a moment, okay? Okay, so I think we can start now. Apologies again for the delay. All right, so tonight we're going to be looking at key maps. I think that was where we ended it last time, right? So we stated that at the continuation of the session, our focus or emphasis is going to be on key maps. Okay, so I think I'll have another session on Friday. So tonight we are going to focus on understanding key maps, solve questions into it, and then look, and then the basic thing we want to understand is how to use key maps to simplify Boolean expressions. So we want to look at expressions and understand how to apply the rules to simplify Boolean um, expressions. So we look at various examples, giving different scenarios, and then how you will be able to use our K-maps to simplify them. Okay, so we looked the last time how to use Boolean laws to do our simplification. And if we are to do your simplification right, um, your simplification for the Boolean, using Boolean laws and then K-maps should return the same value. Okay, so now let's look at K-maps. Okay. So we'll brush through the slides very, very fast, highlight the rules, and then we look at practical problems under K-maps and then how to approach them or how to solve them. Okay, so we said that when given a Boolean expression, you can use K-maps to perform our simplification. Okay, so K-maps are also referred to as 2D truth table representations. Hence, they can only be used to simplify Boolean expressions, which has up to 5 variables. Anything beyond that, K-maps cannot be used to simplify them. So the number of cells that our K-maps can take is denoted by 2 raised to the power n, where n refers to the number of variables in that particular K-map. So if you are given, for example, a function of the sort f, okay, and then you have x, y, and then z, okay. This is literally 3 variables. We explain what variables are in our subsequent or in our previous sessions. I mean, so we have x, y, and z being our variables here. Please, in case you were not at those sessions, or there is anyone here who did not take part in any of those sessions, you can please let me know so that I know how to approach this so that I can still understand regardless. Else, if you are just to go in that manner and you weren't at those sessions, you might find it difficult. So please, if you weren't there, you can just signify or you can just, let us know, or we take it as we were all at the previous session. So you already know what variables are, how to identify the unique, the variables in an expression and so on. So in this case, we have 3 variables, right? We have variable 1 being x, variable 2 being y, and variable 3 being z, okay? So since we have 3 sets of variables, the total number of members or the total number of cells that our K-map can contain will be equal to 2 raised to the power 3, which gives us 8. So it means that that particular K-map for this function is going to be a 2x4, okay, K-map. This would be able to account for all our A cells that can be contained in that particular K-map. So we said, so we are saying that the number of cells in the K-map is determined by the number of input variables n given by 2 raised to the power n, when n is our variables. So if you want to know which type of K-map you are to use, or which type of K-map you are supposed to use to solve a particular problem, first ask yourself, how many variables do we have in the expression or in the problem? And then take 2 and raise it to the power that number of variables, and you'll be able to know which type of K-map you should use. So for example, if you have only 2 variables, let's say a function of the kind x and y, okay, this has only 2 variables. So we are going to have 2 raised to the power 2. Okay, so we know we are going to use, our K-map is going to have 4 cells. So the suitable K-map is going to be the 2 by 2 K-map. Okay, if we have an expression which is presented in the form, let's say A, B, C, D plus A prime, B prime, C prime D. Okay, this particular expression that we have here contains 4 variables, and we all know why there are 4 variables, right? Because the variables there are A, B, C, and D. So if you want to know which type of K-map we are going to use, we take 2 raised to the power 4, right? And 2 raised to the power 4, what does it give us? It gives us 16, right? So we know we are going to use a 4 by 4 cell K-map, okay? And this will be able to account for that particular expression. Please, I believe we are all okay with this. Please, are you all okay with this so far? Please, are we all okay? Okay, someone said I should go over. Okay, so let me go over that again. So, what have I done? So this is what I mean, okay, that you can be given different type of expressions. Let me use a clean sheet for that. So you can be given different types of expressions, right? And you'll be told to simplify the expression, but they will not tell you the type of K-map you should use. The expressions can be given in different forms. Sometimes it can be in the form of raw expressions. Sometimes they will give you the mean terms. Okay. So assuming you are giving something like f is equal to, so let's say you are giving an expression that contains the mean terms as, sorry, let me represent this properly. So you are giving something like f, I'm coming. So these are how most often questions and other things will appear. You are giving something like f into brackets x, y, comma, z, okay. And you are told that the set of mean terms, okay, for this particular expression, you have 1, you have 2, you have 8, you have 5, okay. So this is what you have. Or sometimes if maybe it's a don't care, you have something like plus, then d whatsoever. Okay, but let's assume it is not that. So you have something like this. Okay, so to be able to determine which type of K-map you are going to use to solve this particular problem, or you are going to use to tackle a problem like this, we are going to first ask ourselves that how many variables are contained in this particular expression that is given here. So if you look at this particular expression, we've been told that the function has 3 unique variables, which is x, y, and z, right? So how many variables do we have? We have 3. Okay, so variables are just the set of all unique members of an expression. And here, what are the set of all unique members? They've been defined by the function f of x, y, and z. And f of x, y, and z, x, y, and z are the set of all unique members of that function. So we have 3 variables, right? So if we want to know the type of K-map we are to use, we are going to use 2 raised to the power n. In this case, we are going to use, we know n is 3 because the types of the unique variables we have is 3. So we have 2 raised to the power 3 here, which gives us what? 8. So we know that for this particular expression, we are going to represent it on an 8-cell K-map, okay? And an 8-cell K-map, we know is most likely to be 2x4 K-map, right? So 2x4 K-map, we are going to draw it in this order. So we have 1, 2, 3, and then we have this right here, okay? So we can decide to represent this as, however, as x here, y, and then z right here, right? I believe you know how to continue from here. So we know here is 0, 0. And we stated the last week that the numberings of the cell, we use gray codes. We don't use binary numbers. Let's take note. There's a difference between gray codes and binary numbers. If you remember last semester, we explained that gray codes are a special types of numbers, okay, which differ. Okay, so the difference between a number and its adjacent number is just 1 bit. Okay, so we have 0, 0. The next one will be 0, 1. Okay, so you see, if you are dealing with binary numbers, after 0, 1, you might be tempted to say here is 1, 0. But then when you are looking at gray code, the difference between 0, 1 and 1, 0 is not 1 bit. Why? Because you can see that the first bit 1 has been, a 0 has been changed into a 1, right? So there is a change in the first bit, and you look at the second bit has also been changed. So there are 2 different changes in their bit, which gray code does not permit. Gray code only permits up to 1 change or 1 difference in bits for adjacent representations, okay? So if we want to follow the gray code numbering system, we cannot say this cell, this particular section should be numbered 1, 0, okay? We say it should be numbered 1, 1, okay? And then the last box, we can say this should be numbered 1, 0, okay? Because 1 is maintained, and then this one changes to 0. You can say that it differs only by 1 bit. I believe we all get that. So we come here, and then this x is singular, so we label it by 0 and 1. Okay, so let's take note of this. You see that here, we said here 0, 0, 0, 1, 1, 1, 1, 0. All the first digits or all the first bits you see here represents y, okay? And all the second ones you see here, they represent z, okay? So it's very important that you know how to locate y and how to locate z, although that particular field has been labeled as yz or yz here, okay? But the first bits are for y, and then the second are for z, okay? So let's just finish everything by just plotting our values here, okay? So what this question is telling you is that if you take 1, okay, if you take 2, if you take 8, if you take 5, this particular cells, the cells with those numbers, they have a return value of 1. A return value of 1 means that identify those cells and put 1 there, okay, and everything else have every other cells are deemed redundant, or they practically do not affect our expression, okay? They do not necessarily have a return value of 0 but they have no impact on our expression, so we don't even consider them at all. Okay, so let us look at what we mean here. So in numbering the cells, let me give you this trick here. Most people might be tempted to say, okay, this cell is cell 1, this cell is cell 2, this cell is cell 3, this cell is cell 4, this cell is 5, this cell is 6, 7, 8, or whatsoever. Sorry, we always start numbering from 0. So someone will say this is 0, this is 1, this is 2, this is 3, but it does not work like that, okay? Because we said that the fields were numbered using gray codes, we want to actually represent the cells using the actual binary equivalent. So we say this box is 0 because we know 0, 0 is 0, right? 0, 1 is 1. But the problem is that when it comes to 1, 1 here, 1, 1 in binary, okay, has an actual equivalence of 3, okay, and then 1, 0 is 2. So we can see that the original location of this cell is 0, this is 1, this is not 2, this is 3, not 2. Okay, so this is 3, and this is rather 2. Okay, and the reason why they are so is that we used gray codes to represent the field or to number the fields. But then when we are dealing with the original cell numbers, we want to look at their actual representations. Okay, so if you are to say here is 2, then you might be making a very huge error, because if you look at the original equivalence of 1 and 1, it is actually 3 and not 2. Okay, it is rather 1 and 0, which is 2. So if you come to the next box, it follows suit. Here becomes 4, here becomes 5, and this will not become 6. Okay, this becomes 7, and then this becomes cell 6. Please, do we get that? So I'm coming 1, 0, 1, 2, 3. Let me erase this and then replace it with 7. Okay, in order for us to get everything right. So please, I hope we are okay with the cell numbers and how we deduce these numbers for the cells. Please, are you all okay with that? Please, if you don't understand or if you have a problem, just let us know and then we would look at it again. Okay, I think we are here to understand everything. So it's just very right if you don't.
Hello, sir. Good evening.
Evening, please.
Yeah, please. When I checked, I heard you saying that you use the power of the number to determine the cell.
You said I said you use the power of the number.
Yeah, I mean, when I
No,
check
no,
the
no, no.
numbers,
I did not mention the power of the number. When it comes to the only place where we use powers is to determine the total cell numbers or the total cell numbers we are to use for that particular K-map, not the cell
oh, okay,
numbers.
okay.
Yes,
So,
please.
here, for instance, I can see 1, 2, 7, and 5. So that one, the numbers are 4. But then, when you draw the K map, it was you use 2 raised to the power 3 instead of 2 raised to the power 4. So I was a bit confused.
Oh, okay. So
Yeah.
let me denote that again, okay, or let me explain that again. So to determine the particular type of K-map to use, so to determine a particular type of K-map to use, you look at the number of unique variables you have in your function. Okay, so in this function, we have X, Y, and Z. So in this function, we have X, Y, and Z, where X, Y, Z as your number of variables. We stated that variables are the unique members of an expression. Okay, so here, the unique members are 3, which are X, Y, and Z. So since we know our unique numbers, we represent it by N, okay? So if we want to determine which type of K-map to use, we take 2 and raise it to the power the number of variables, which in this case is 3. So 2 raised to the power 3, which is 8, made us know the number of cells we needed to represent or to draw a K-map for this particular function we've been given. Okay, so we used the variables given here, which is, if you see the question, you see it here. Sometimes you can be given a raw expression. When we are done with that, I'll take an example of that also so that we'll see how that differs for this. For this, you've been given the mean terms instead of the actual raw expression. Okay, so this represents the mean terms which has a return value of 1. So they are saying that you have to locate box number 1 or cell number 1, cell number 2, cell number 7, and cell number 4. And in those cells, you are supposed to plug in a value of 1. So we come to cell number 1, we plug in a value of 1. We come to cell number 2, we plug in a value of 1. We come to cell number 7, we plug in a value of 1. And then we come to cell number 5, we plug in a value of 1 also. Please, I believe you can see that. So all the other cells, we leave them as null and void because we take them as redundant. They do not impact our final expression, or they have no impact or effect on our final expression. So they are basically or typically ignored. Okay. So please, are we okay now? Or someone
Yes,
still
sir.
has a question?
Yeah, yes, sir. I get it now.
Okay. So after we've denoted our boxes or our cells, that corresponds to the mean terms we've been given. You know, remember, this is M1, right? If we want to expand this, this is M1, this is M2 plus M2 plus M7 plus M5. This is what this originally represents. Okay, this is what this original here represents. And you can go ahead to draw, to deduce an actual function for this here. Okay, to deduce an actual function, I don't want to complicate things, but to deduce an actual function for M1, you basically have to take all set of inputs, which let's not look at that. I think we will complicate things. Let's finish the question, and probably if we have time, we look at that. So the rest of the boxes, we leave them as null and void. Okay. And then now, when we look at the rules or the laws for K-map, we say something that we can only circle or select squares which are adjacent to each other, okay, or which are next to each other, okay, but we cannot select diagonal cells, okay. So for instance, you cannot do this. This is not allowed when you are selecting your cells, okay. This is not allowed, but this here is allowed. So you can select them in this manner. It's allowed, okay. Again, another rule states that in case you have a 1 here, you have 1, 2, 3. So someone will be like, oh, this is a 1, a 1, and a 1. Let me just select these 3 boxes. This is practically wrong. Okay, in K-maps, you can only select your cells, okay, with a return value of 1 in the powers of 2. So 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, etc. That's another rule that we always have to remember. So 2 raised to the power 0 is 1, right? 2 raised to the power 1 is 2. 2 raised to the power 2 is 4. 2 raised to the power 3 is 8, okay? So this means that you can only select either one box, one cell at a time, 2 cells at a time, 4 adjacent cells at a time, or 8 adjacent cells at a time. But you cannot select in between. For instance, if you have 3 adjacent cells, you cannot say because these 3 cells are adjacent to each other, you are selecting them. It is not allowed, or it is considered illegal, okay? You can only select 2 adjacent cells per time. Or somebody will also say that, okay, since we can select 2 cells at a time, let me select this. Oh, what have I done? So let me select these 2 diagonal cells. What am I even doing? Let us select these 2 diagonal cells, right? It is not also allowed. You are not allowed to select in this manner. Okay. Selections are supposed to only be done for 2 cells at a time, or 1 cell at a time, or 4 cells at a time which are adjacent to the other. And please, the cells can also wrap around each other. We will explain all those things as we move forward, but let us complete this question. So for this particular instance, we can now say that we've been able to create our K-map representation for this particular problem here or function here. So after we have this, we might be asked to simplify it further. If the question should ask you only for the K-map, then you are cool with this. But if the question should ask you to simplify this further, then this is what you are going to do, okay? You see these two cells are literally adjacent to each other. You can highlight them. These two cells are so, you can highlight them, and this cell is singular. You can literally circle or select this cell also, because you can select one cell at a time, two cells at a time. And please, if cells overlap in this manner, we still select them, okay? Overlapping cells are allowed, or we can select cells that actually do overlap. And then if we have this here, I said something earlier that if you have YZ here, all the first values or all the first zeros are Y values, and the second is Z values. So you see, this is the first cell we circled. So we come and compare this to our the corresponding field the corresponding field value, okay? So we have 0 and 1 right there. So for 0 and 1, we take 1 and 1, and then we compare it to 0 and 1. So we first compare 1 and 1 to 0 and ask ourselves that how do we create a representation for 1 and 1 relative to 0? We know 0 is y, right? Or we can call 0 y prime. So we have 1 and 1 here. To make it correspond to 0, we invert it. And to invert it, we just write y, and then we put a bar on top, okay? And then we can do the same comparison for our, how do you call it? Our z value. And when we compare, z is a 1, so we have our z value. But when it comes to our x, you can see that your x is changing. It's moving from 0 to 1. There is no way you can manipulate it to create a 1 and a 1 here. So it means that this particular expression here, or this particular term here, is independent of x. So you ignore that. Then you come to the next selected adjacent cells, okay? So this is 1 and 1. So if you compare this with your x, you realize that the corresponding x value is also a 1, right? So we bring our x here. Now, if you take this and you compare it to the upper fields, you realize that we have 0 and 1 and we have 1 and 1 here, right? So now let's compare our 0 and 1 here, which is the y values. If you compare this for the y values, you realize that y is changing. And whenever you have a specific value changing, you ignore it. It practically means that these adjacent cells selected are independent of y. And then we come and check the next one, which is 1 and 1, which is the corresponding z values. So if you come and check, you realize that 1 and 1 is static. And then the expression, the cells selected are also 1 and 1. So it means that they are dependent on z. And we don't have to invert them because they are the same as the selected cells here. So we repeat z right here. Okay. So apart from that, we have a 1 here also. So if we can compare this one to our x, our y, and literally if we are to compare, our y here is seen, but it's inverted, okay? Our z here is present, not inverted, and we can see that our x here is present, but in the inverted form. So from this, we can be able to deduce that the corresponding expression for this particular problem here is x bar z plus x z plus y bar z x bar, and that becomes our final answer for this particular problem. And we can be able to say that this particular expression here is in its simplest or simplest form. Okay. So please, do you all understand what we just did here? Or someone has a question or a problem? Or you want us to take everything again? You can also let us.
Yes, please, can you take it again?
Come again.
Yes, please, can you take it again?
Okay, I should take it again. Okay. So let me take this again. So let me write a question somewhere. We have f of x, y, z. Your mean terms are 1, 2, 7, and 5. Okay, so let me refresh the screen. Okay, so we have a function that contains x, y, and also has z. And then we have a sum of mean terms with corresponding values of 1, 2, 7, and 5. Okay. So this the problem that we worked with. Okay. What is a problem that we worked on? So I think the main reason why this looked a little bit complicated is because we went straight forward to an A cell came up. Okay, so I might have to explain everything from the very beginning, or how came up work, and then we'll solve this question, this same question. And I believe that after doing that, the question might be much direct and make much meaning. Okay, so we are saying that K-maps can be represented in different forms depending on the problem that we are given. Okay, and to be able to know the type of K-map you are to use to solve a specific problem, we first have to look at the number of variables within that K-map. So depending on the number of variables, we can have a 2 by 2 K-map. Okay, so we can have a 2 by 2 K-map. Okay, so a 2 by 2 K-map is simply a K-map which has two variables, because we are saying that if you want to know the number of cells to use, we take 2 raised to the power n. So if the variables are 2 raised to the power 2 will give you 4. So to represent 4 cells, a 2 by 2 K-map is needed. So a 2 by 2 K-map for the function A and B, where a function with variables A and B can be represented as you have this right here. We said 2 by 2. That means that the total number of cells are 4. Okay. So you have this right here. Okay. So this is a 2 by 2 K-map. They have a total of 4 cells in them. Okay. So to represent A and B, we can denote this place as A and then denote this place as B. So it means that the fields at this section will be denoted as B, and the fields here will be denoted as A. Okay, so to number the fields, we use gray codes to do our numbering. So gray codes are basically a binary numbering system where each number or each representation differ from the adjacent representation by just 1 bit. Okay, so you can have 0, 0 here, and then here you have 0, 1 right here. Now somebody will be like, what does this 0, 0 and 0, 1 here means? It's simple. Oh, sorry. What was I thinking about? Please forgive me. Please, you are dealing with a 2 by 2 cell K-map. There is no need saying 0 and 0, just 0 and 1 is enough for us. Okay. So you have 0 and 1 for B, you have your A also being 0 and 1. Okay. So this means that the box value for this here will be 0 and 0. The box value for this will be 0 and 1. The box value for this will be 1 and 0. The box value for this will be 1 and 1. And I'll explain that in a moment. So 0 typically, we know 0 typically with relation to B. We know everything here is B, right? So 0 here with regards to B is B complement, okay? You have B. B is 1, okay? So that means that B prime will be what? Will be 0. So that is the meaning of everything you see here. A, if A is 1, then A prime is what? 0. That's A naught. Will be the, I mean, if A is 1, then if A is 1, then A prime will be equal to 0, okay? So you see the B you are seeing here, the 0 you are seeing here technically represents your A. And then the 1 technically represents A prime, okay? So you have A prime right here. And then the 1 here that you see technically represents your A, okay? So let's take note of that. That's the reason why I remember this 0 and 1. Technically speaking, these are actually A prime and this is A. And this 0 here is also A prime. This one, oh goodness, what is happening to me? So please, here is not A prime and A, here is actually B prime in this place. So we have B prime, because you said all this field is actually B, not A. And then we have B right here. So 0 here, you have A prime, and 1 here becomes A, okay? So we are saying that this box here, if we are to pair properly, this box here becomes 0, 0. So what does 0, 0 mean? 0, 0 also means A complement, B complement. So it means that this box, everything that is held in this box represents A complement, B complement, okay? Everything held in this particular box represents A complement B. A complement B. Everything held in this box represents A, B complement, or B prime. And everything held in this box represents A, B, okay? If you have to use X and Y, it also gives you the same. So you can see that 0, 0 here, represented in this cell, actually means A complement, B complement. 0, 1 here means A complement B. 1, 0 means A, B complement. And then 1, 1 means A, B. So the cell numbers are technically made to address the specific contents of the cells. They are just not coincidental, okay? But they are intentionally arranged in that order to properly represent the content of those cells, or what those cells will house, or what those cells will contain. Now, if you want to number these cells with regards to our mean term values, we will call this cell cell 1, we will call this cell cell 2, we will call this cell cell 3, and we will call this cell cell 4. I mean, we'll call this cell cell 1, we'll call this cell cell 0, okay? Please, when I'm reading, always start from 0. We'll call this cell cell 0, we'll call this cell cell 1, then we'll call this cell cell 2, and then we'll call this cell cell 3. How do you know that this cell is cell 0? How do you know this cell is cell 1? How do you know this cell is cell 2? How do you know this cell is cell 3? Just look for the binary equivalence. So here is 0 and 0. 0 and 0, literally, the decimal equivalence is 0. 0 and 1 is 1. 1 and 0 is 2. 1 and 1 is 3. So you know that is the actual values that those cells will hold, okay? Or when you're arranging your mean terms or anything in there, those are the cells we are looking for, or those are how the cells are numbered. It is important to know the cell numberings because it is almost impossible to be able to solve questions without understanding or knowing how the cells are numbered. So in the case where you are having a 2 by 4 K map, which is another type of K maps, okay? In the case where you're having a 2 by 4 cell K map, this is a K map which has 3 distinct variables. So if we are having 3 variables, automatically you have a total of 8 cells because 2 raised to the power 3 is 8. If you're having 2 variables, you have 4 cells because 2 raised to the power 2 is 4. Okay. If you are having 4 variables, you have 16 cells because 2 raised to the power 4 is 16. So to be able to know the number of cells that you need to address that function, you just look at the number of variables and then you take 2 raised to the power the number of variables contained in the function. So if you have the function x bar y z all plus x y plus, let's say, z bar, okay, this is a simple function, or this is a simple function, okay. To be able to know the number of cells that you need to address this function in a K-map, you just have to ask yourself, how many variables are here, okay? So in this particular expression, you can see x there, you can see y there, you can see z there, okay? So we can say that this particular expression here has a total of 3 variables, which is x, y, and z. So we now take 2. A second. Okay, so we now take 2 and then raise it to the power the number of variables or the number of unique variables we have. In this case, you have 2 raised to the power 3. And 2 raised to the power 3 gives you what? 8. So you know that you need, in order to address this function correctly, you need a K-map with 8 cells. You are seeing it. So you cannot use a 2 by 2 K-map to address this particular problem here. Assuming you meet this question in the examination and you are told to simplify this using K-maps, you cannot use a 2 by 2 K-map to simplify this problem here. You have to use a 2 by 3 K-map. Why? Because this expression has 3 variables and 2 raised to the power 3 is 8. That is how come you need an 8-cell K-map to address this problem. And how do we get an 8-cell K-map? We have to be able to draw the K-map in a way that is going to have 8 cells, okay? And to do that, we use a 2 by 4 K-map. Someone might also say, okay, what if I use a 4 by 2 K-map? You get the same thing. Some people prefer to draw their K-maps this way, but sometimes, you know, there are variabilities to it, okay? I prefer using a 2 by 4 instead, okay? So you divide this into 2, then you have this way. Now count the number of cells. You have 1, 2, 3, 4. You have 1, 2, 3. Okay, I'm left with one more box, right? So we have 1, 2, 3, 4, 5, 6, 7, and 8. So realize that this particular K-map here that you've drawn here, or this particular table you've drawn here, is able to address all 8 cells that are needed to represent a 3-variable K-map. Okay, so we use this particular type here for 3-variable K-maps. Okay, so assuming the problem has your X, Y, and Z, you can represent this as your X, then you represent this side as Y and Z. Okay, so when numbering your fields, you are going to say that this first one is 0 and 0 because you are using gray codes. you are going to say that this is 0 and 1. You are going to say that this is 1 and 1, and you are going to say that this is 1 and 0. Please, you don't say this is 1 and 0 and this is 1 and 1. It is wrong. This is the reason why I'm saying it is wrong. It defies the laws of K-maps. The rule says that each field number, okay, should differ by the other, should differ by the adjacent field by just 1 bit. So if you are to say here is 1 and 0 and here is 1 and 1, then you are defying or you are going against the laws. This is why you are going against the laws. Let's dive into this, or let's dissect this. You have your Y value. We said, please, all the first are Y values. So this here is your Y values. Let's call this Y0. Okay, this here, Y1. All this, the first ones are Y values. And the second one are Z values. Okay, so this is Z, Y. This is a Z value. The first is a Y value. Second is a Z value. First is a Y value. Second is a Z value. So that is how you're able to know, or moving forward, it becomes very important that you know that the first number here is your Y value, second is your Z value, Y value, Z value, Y value, Z value, Y value, Z value. Okay, so we're talking about why this numbering system defies the laws or the rules for K-maps. If you take 0 here, you can see that this 0 here has been changed to a 1. And this 1 here has been changed to a 0. So we've now manipulated 2 bits. But the law is saying that we can only change 1 bit when numbering our fields, not 2. So if we go to number 2 bits, we go to change 2 bits as we have done here, we've defied the law, and everything you are going to do is basically against the rules for K-maps. And you most likely end up with a result that you don't need or you don't have to get. Because at the end of the day, you are going to insert or plug in your ones. And you need your ones to be properly adjacent to each other in order to be able to deduce their expressions right. But if you number them wrongly, you are going to insert the values wrongly also. And then at the end of the day, your final output is going to be a mess. Your final output is going to be a mess, okay? So to solve this problem, we make sure that our numberings are done using gray codes, okay? So we have 0, 1 here. Here becomes a 1 and a 1, okay? And before this place becomes a 1 and a 0. The gray code system defies the binary numbering system because they do not accurately represent binary numbers. But when it comes to graphically and visually, it's able to create the right impression. Why do I say so? Because it follows a specific pattern, and the pattern is that each adjacent bit differ from the other by just 1. Okay, so if we now have this, how do we know which box is box 1? How do we know which box is box 2? We know that this is box 1. We know that this is box 2. But we cannot say, sorry, we know that this is box 0. I've always been making this error. We know that this is box 0. We know that this is box 1. Okay, we know that 0 and 0 is 0, 0 and 1 is 1. We know that this is box 1. But then we cannot say that this box is 2. Because if we try to look at the binary representation of this, we know that this rather becomes your 2, not this. Please, let's look at this very well. This cell here becomes your original cell 2 instead of this. We've technically swapped these two. This one was originally supposed to be here, and this one was supposed to be here. But since we were following the gray numbering system, we were supposed to we exchanged these two and brought this one, which was supposed to be here, to this place, and this one rather to this place. So when numbering, we have to make sure that we identify this as cell 2 properly and this as cell 3 and not otherwise. Okay, so it's very important that you're able to know the specific location of the cells, because most of the times when you are being given questions and they give you the mean terms, they are going to give you the cell numbers or the corresponding cell numbers, and you are supposed to know that if the question tells you, okay, that the return value of cell 2 is 1, you know that this is cell 2 and not this. So you don't come and put the 1 here, but you rather put it here. So it's very important that you know this. Okay. So this becomes your 3, this becomes your 2. And then you come here, you do the same thing. So now that we've read the maximum of 3, we know this here becomes our 4, right? This here becomes our 5, but we cannot say this is 6, okay? The reason why we cannot say this is 6 is that we are saying that this particular field 1, 1, and 1, 0 have been swapped for each other. So instead of saying this is 6 and this is 7, we rather say this is 7 and this is 6, because we know that the original positions have been swapped. Please, I believe we are together with this. So this is how how you can accurately determine the position of your cells and how to number your cells correctly and accurately. So let's look at how you can be given a question with this instance and how you can be able to solve this. You can be told that you have a function f of f, and f has 3 distinct variables, x, y, and z, okay? And then it has the mean terms 1, sorry, what am I doing? Sorry. So we have brackets right here. It has mean terms 1, m1, okay, has a positive output, has an output of 1. We have we have 4, and we have, let's say, 6, okay? So you know, now we've been able to number our cells properly. So as we're able to determine our cell numbers properly, you just have to ask ourselves, why is cell 1? This is cell 1. So we insert a value of 1. Why is cell 3? This is cell 3. We insert a return value of 1. Why is cell 4? This is cell 4. We insert a return value of 1. Why is cell 6? This is cell 6. We insert a value of 1. As simple as ABC, okay? Or this is just simple and straightforward. If you're able to properly know or denote the number of your cells, okay? Please, I hope we are all together up to this point. So let's take questions before we continue. Okay. So any problem? If not, then we continue. All right. So if no one has a problem, then we can continue. Okay. So let's now assume that this particular cell here is not a 2x4 K-map. Let's convert this to a 4x4 K-map. When do we use 4x4 K-maps? We use 4x4 K-maps if we have a total of 4 unique variables, okay? So what do I mean by 4 unique variables? You are given a problem set like x, instead of x, y, and z, you are given w, x, y, z for your function, okay? Or if you are given an expression, you are given something like w, x bar, y, z plus w, y, z plus, let's say, w bar, y bar, z bar, okay? So how many variables do we have here? So how many variables do we have? Someone can unmute and tell us.
Four.
We have 4 variables, right? We all agree with that. So we have w, x, y, and z. So we have 4 distinct or 4 unique variables right here. Okay. So if you want to know which type of K-map we are going to use, how are you going to know which type of K-map we are going to use? Please, can someone help us?
2 raised to the power 4.
Sorry.
2 raised to the power 4.
2 to the power 4.
All right. So we have 2 raised to the power 4, right? And 2 raised to the power 4 is what? That's 16, right?
16.
So we know we need a 16 cell K-map. And to be able to draw a 16 cell K-map, we make it 4x4, right? So a 4x4
Exactly.
K-map.
Exactly.
Yeah, so that will be able to properly account or settle this. Please, are you together?
Yeah, we're together. Let's go.
All right. So now let's just convert this. I want us to maintain this for a reason so that we are able to understand the numbering system for an 8-cell K-map and how it differs from a 16-cell K-map. So we just extend this to add, it's already 8 cells, right? So we just need to add 8 more cells. So to add 8 more cells, we can just do this. And then we add one line to this. We now have a 4x4. So 4x4, we can see that we have 1, 2, 3, 4, 1, 2, 3, 4, right here. Okay. So now we have to renumber, we have to relabel this. Okay. So instead of saying this is X and this is Y and Z, we now have a new variable. We have W. So we can say here is W and X. Okay. So here is W and X. So we know that here will be 0 and 0. Here will be 0 and 1. Here will be 1 and 1. And here will be 1 and 0. And this is where it gets a little bit tricky. Okay. When you are numbering, you have, we ended here. We said here is 0, 1. This is cell number 3, 3, 2, 4, 5, 7, 6. Now, when we get here, somebody will say that, oh, we are continuing from 8. Here becomes 8. That's not true. Someone will say here will become 8, here will become 9. Then these two has been swapped. So we say this is 11 and this is 10, but this is very untrue. Why is this untrue? You see that we said that 11 and 10 here have been swapped, right? 11 and 10 have been swapped, right? The same way here also 11 and 10 have been swapped. Can you also see that? It was originally supposed to be 10 and 11, but we've swapped, we've changed their positions. So that means that instead of numbering here 8, 9, 10, 11, you are supposed to rather come a number here 8, 9, then here cannot be 10, right? Here becomes 11, here becomes 10. Before we now come here and say here is 12, here is 12, here is 13, here is 15, and here is 14. Please, did we all get this?
Yes.
Okay. Okay, so the reason why we didn't label this place 8, 9, 11, 10 is because the same way we established the fact earlier that these two positions have been swapped. Hence, we'll send the original values to this place instead, and then we move the value from this place to this place. That's the same thing we are doing for this. So this was supposed to be 8, 9, 11, 10, but it has been moved here rather. So to 8, 9, 11, 10. And the original one that was supposed to be here has been moved here rather. So we do that to accurately represent the swapped position. So this becomes a 4x4 K-map. All right, so a 4x4 K-map, there are several ways to number this. You can also decide to number it with its corresponding binary computation, that is 0, 0, 0, 0, because this holds values for this, or the point where W is not, so W not, X not, Y not, Z not, okay. And this here represents what? 0, 0, 0, 1. So we have 0, 0, 0, 1, right? 0, 0, 0, 1 is what? W not, X not, Y not, and then Z. And then if you come here, you have 0, 0, 0, and 1, 1. So you have 0, 0, 1, 1. That is W not, X not, Y, and Z. And then here you have you have 0010. So that becomes W naught X naught. Then you have Y, and then you have Z naught. Okay. So you can continue to label the rest of the cells in this manner. So there are several ways to label these cells. Okay. And each of these, you just have to master one style of labeling, or you can master two, and then know how to plug in the values. For example, if you are given an expression, you should know how to plug in the values into this whole thing, and then you'll be fine. Please, any questions so far? Any questions so far? Any questions so far? Any questions so far? All right, then we can take it as everyone is okay. Yes, Mr. Freeman.
Yes, please. According to the table I was seeing, you said
Okay.
I had to change the position of the 10 and the 11. And the whole
Yes, sir.
purpose of that is to make there be a difference in one bit position.
Yes, please.
Okay, so for the 0, 0, and 0, 1, I'm seeing a one bit difference in position as you stated. But
Okay.
do we compare the last two, or I compare the 0, 1, that is the second one, and the third one as well, or the comparison is done 2 2? That's the only thing I'm confused. As in, the
Okay. So,
comparison was done between 0, 0, and 0, 1. So the next one was done between 1, 1, and 1, 0.
okay. So I get you. I get you. I get your question. So if I got you right, you're asking if the comparison, okay, so let's say 0001. If the comparison is done between, sorry, between the first bits or the second bits, right?
Yes, in that manner. And
Okay.
then I'm asking if the first one, just the comparison between the first and second. Okay, is the comparison also done between the second and then the third as well, as in the one on the next table?
Okay. So basically the comparisons are done between the bits and its adjacent bits. Okay, they have to differ by one. For this one here and this one here, they might not entirely be true most of them, but the consideration is mainly between the representation and the next adjacent representation. Yeah, so
If that,
we
yeah.
wouldn't consider comparing, let's say, a bit and a representation and an unrelated representation. We just want the next adjacent representation or the representation
So,
before that one. So, for instance, the representation here has to differ from this representation here by a bit. The representation here has to differ from this by a bit. If we do not do that, example, comparing this one here to this one here might create an issue because comparing 0 and 0, you can see that this differs, and then 1 and 0 also differs, and it does not meet the rule. So the rule states that the change has to be between two adjacent representations.
okay, so two adjacent representations. So that is
Yes,
if I'm
please.
looking at the second and then the third. The second one
Yes,
you have circled, and then the third, that is the 1, 1. I'm seeing
yes,
0, 1, and 1, 1. But the one by the 0 and then the first one, and they the same. Or am I doing the comparison wrong?
Okay, so you are talking about this one and this one, right?
Yes, please.
Okay, so yeah, so 0 and 1, there is a change in bit, but 1 and the 1, the bit is maintained. So you can be able to conclude that there is a change in only one bit for the adjacent representation or for the next adjacent representation.
Oh,
So
okay.
it's
So
typically satisfies.
if I'm getting it right, that means that it does not necessarily have to be that the one by the 0 and then the first one like being the same, because that's how I thought it would be. As in
Okay,
the
so
one by the 0 and then the first one inside the 1 1. That's how I was seeing it. That's what I was asking. As in being
okay.
the same. Mm.
Okay, so that's not entirely the case. So you literally want to compare the individual bit position with the next individual bit position, and then
Yes,
be able
yes.
to denote one single change in the bits, and then we can say it satisfies gray codings. And thank you, sir. Okay, so I think if we are okay with this, then now we can look at solving questions and problems. Okay, and then on Friday we look at other concepts and this. But for now, with this concept, let's use them to. Our time is getting closer, so let's use them to solve some problems and then see if we've solidified them. All right, so let's take some problems. So let's take some questions. And let's look at them. Okay. So I want to find some questions on all right, so we have the question here. Okay, so no, this come too complex. A second, I just want to get something that is not so complex.
You collect o. Leave the thing.
All right, so let's take this. We have the function we have A, B, we have C. Okay. Then we have M bracket 0, 1, 6, 7. Okay. Plus don't care condition. Oh, please, if you've unmuted, please kindly help us by waiting. All right, so please, this is a simple question. So you have to minimize the following Boolean function. Okay, so we have to minimize this Boolean function. I think this will help us maybe explore one more concept. And I think after solving this, we might try our hands on one more problem and then we'll call it done for the day. So now let's look at this Boolean expression. Function right here. We have a function that has 3 unique variables. So the first thing that we can deduce from this question is that this is a 3 variable function, right? And if we have a 3 variable function, we know that we are going to use an 8-cell K-map, right? So this our first deduction, right? Because you know that we have 2 raised to the power 3, which gives us 8. So we can now proceed to draw our K-map. So we have 1, we have 2, we have 3, and then we have this right here. Okay. So we know that the variables are 3, right? So we can decide to represent A here, and then we have B right here, and then we have our C. Okay, and then let's label this. We have 0, 0. We have 0, 1. We have 1, 1, and we have 1, 0, and then we have 0, 1. So before we proceed to even start anything, this is the first thing we know we have to do because this is a 3 variable K-map. And for the variable A, B, and C, we know that this should be the framework of our K-map. Okay. So now what is it saying? The first thing here is saying that we have our mean terms with a return value of 1 for the cell 0, right? We know this is 0. So we can label this is 0. This is 1. This is 3, right? So I believe as of now, we know why this is 3 and why this is 2. And then this is 4. This is 5. This is 7. And this is 6. So where are we going to put our 1? So 0 takes 1, right? So 1 takes 1. So 6 takes 1. And so 7 takes 1. Now, what is the last part of the question saying? You can see something like plus, then summation of D brackets 3 and 5. The D here means don't care. Okay. I added this here. If it is not there, then we had already represented everything here already. But since this is there, then we have to understand what this is telling us. This is a don't care condition. That means that for cell 3 and 5, this is our cell 3 and 5. Our cell 3 and 5. It can literally take, let me simplify what the don't care cells mean. It means that these cells here can literally take values of either ones or zeros, okay? So if in the question you are giving mean terms, you just assume they are 1. If you are giving max terms, you assume they are 0, okay? So now we are going to consider our don't care cells as well, because we don't care what the values of those cells are, but we are going to consider them in our representation. So psychologically, we know this is a 1, this is a 1, okay? Or you can decide to put it there, but usually for don't care cells, we put X or we represent them with X, okay? But when we are selecting our adjacent cells, we are going to select those ones as well. Please, let's take note of that, okay? So for this particular problem, if we are to select our cells, we would have done a 1 and a 1, right? If assuming there was no don't care condition, we would have done a 1 and a 1, and then we would have done a 1 and a 1. We said we only select adjacent cells, right? That has a return value of 1, or that has a value of 1, okay, in the cell. And then we can select 1, 2, 4, 8, 16 cells at a point, but you cannot select 3 cells at once. They are not allowed, or it basically defies the rule. We cannot select 5 cells at once. It defies the rule. So here, this is correct because you have 2 adjacent cells. Correct because you have 2 adjacent cells. Now we know that this right here is the corresponding B value. This here is a corresponding C value. This here is a corresponding B value. This here is a corresponding C value, B value, C value, B value, C value. So we are going to inspect the cells that we have circled or we have selected to their corresponding A, B, and C values and see if they are positive or they are negated, or if they are redundant. That is, those inputs, which is either A, B, or C, do not apply to those particular cells at all. So let us look at this. Let us look at this. You have 1 and a 1 here, right? If we trace this to our A values, what are we going to see there? We can see that our A values have 0, right? So if you compare a 1 and a 1 to 0, you know that a 1 is an inversion of 0, right? So we invert our A. That's all. Okay, so we invert our A to represent the corresponding A value for these 2 adjacent squares that we've selected, adjacent cells that we've selected. Please, I believe we all understand why we inverted our A, or why we all said this right here corresponds to A prime to our left. Okay. And then now we take this whole box. You can see that this box occupies 2 cells, right? Those cells have field numbers of 0, 0, and 0 and 1. So we'll compare the first to the first and the second to the second. Please, this is how the comparison is done. Don't compare the first to the second and then the second to the first. You don't do it like that. We compare the first to the first because we said this here is the B value. This first here, all the first numbers you see here are B values, and the second ones you see here are C values. So you want to compare A values to A values and B values to B values, and not A values to B values. So here, if you compare the B values here for the cells that has been selected, you can see that the first B value is 0, the second B value is 0. And what can we do to 0 and 0 to get 1? We invert, right? So we are going to take the inverted form of B in order to get our cell values of 1, right? So we take B naught, or the inverted B's right here, okay? And then we are now done with this box. So we now come to the next 2 cells that we selected. So we selected cell 7 and cell 6, right? Let's trace this to our A values. Our corresponding A value is 1. Now we can see that our A value is already 1, which corresponds to the value of those cells we've selected, right? So there is no need to invert them, okay? We just bring our A because it already corresponds to it, that is 1. Please, if it is 0, you invert so that it becomes 1. But if it's already 1, there is no need to invert. Now let's come up here, okay, and do a comparison. Please, you would note that with here, I didn't even proceed to do the comparison for our C values. Please, let me explain that. I forgot to explain. The reason why I even ignored the C values at all is that you can see that the C values are changing. You have 0 and 1. There is nothing you can do to 0 and 1 to get 1. You have 0 and 1. Okay. If I decide to invert 0 and 1, I get 1 and 0. So you can see that there is no way 0 and 1 can give you input values of 1 and 1. Okay, so it means that this C here has no effect on our expression, or this C there does not affect our expression in any way. So you don't consider C in the final value of our expression there, or we eliminate C, okay? So where the values are changing, we eliminate that particular variable. So when you take 1 and 1, if you come to 1, it corresponds. So we brought A. Now, if you trace it to the upper field, you have the B corresponding B values to be 1 and 1, right? So 1 and 1, it means B applies, right? But let's take 1 and 0 and compare in C, which is the corresponding C values. You can see that C is also changing again. And there's nothing you can do to 1 and 0 to get 1 and 1. So it means that C is redundant for the output of this expression. So we ignore them. Okay. So we can say that the final output of this particular problem here is our A prime B plus our A B prime. Okay. So now we have don't care values of how do you call them, of 0. I mean, we have don't care values of 3 and 5. So we've decided to put x in the position of our don't care values, right? So now let us consider our don't care values. If you consider our don't care values, we literally can select this box here, okay? And then we can also no, we cannot, sorry. We said we cannot select 3 adjacent boxes. We can only select 2 at a time, right? So we can select 1, 2 right here. We can select 1, 2 right here. And we can select 1, 2 right here. And then this one is 1. So we can select 1 here. Okay. So when we decide to derive the resultant, okay, of these boxes, we are going to get a very, very lengthy expression. But technically, if you simplify, you should still be able to arrive at the same thing. So usually, it is recommended that if you have not don't care values, you can decide to select them all right, but you will not get a simplified version of that expression. Okay, you have to still simplify it further, which doesn't make sense. That's why we call those boxes don't care. We call it don't care because we are saying that whatever the output of those particular cells are, it does not really affect our expression. Okay. So whilst you can decide to represent them with either 1 and 1 or 1 and 0, the final output of those expressions will give you a very complex output, or a very complex expression, which in turn has to be simplified further. Okay. So at the end of the day, we can say that this expressions here, which is AB plus AB, A prime, B prime plus AB, whilst ignoring the don't care value, would actually give us a correct simplified version of that expression. If we decide to consider the don't care value as well, you have to perform a slight simplification and you arrive at the same output for our expression. So that is how to solve problems of this sort. Okay. So you can say that the minimized Boolean expression for f of ABC is equal to AB plus A prime B prime. So please, are you all okay with this?
Please, I have a question.
All right, please. You can ask.
Thank you. So I have 2 questions. The first one is the ABC, placing the ABC on the axis. Is it okay to say axis? Hello. You see, we placed A at one side and then the BC at the other. So what
Yes,
happens? What happens when we put AB at the top and then C at the down? Because I realized if we are to put AB at the top and then C at the down, then our final answer would now be A prime C prime plus AC instead of
okay,
A prime.
so your question is what if we decide to, let's say, do this let me see, A at the top right, and BC here. Is this a
So
question?
A B at the
and C.
top and then C down.
Sure. So if we were to decide to do it A here, B, C here, let me just address that. That would have been an impossible scenario, because if we do BC
No,
here,
I
that means
mean
that I understand this, but
that
I'm just trying to.
that's not what that's not what I
All
was
right.
trying to
So
say. I was saying it will be A B at the top instead, then just C at the down.
yes, please. I think I very much do get you. I was just trying to address that scenario. If probably someone might make that
All
mistake in the future.
right.
Yeah. So please, I was just trying to say that if you are to put A up there and then BC down there, you have to flip the table to a 4x2 map instead of a 2x4 in order to address all cells properly. So let's work with what and let's see something right here. So we have a case where somebody attempted this, okay, or our brother attempted so we have 1, we have 2, and we have 3, right? So we have A, and then we have C, right? Is this is what we did, right? Hello, boss.
Yes, sorry, my network is breaking. Yeah, that's what I did. Thank you. That's what I did.
Okay. Okay. So let us attempt this, and then let's see. So if you attempt to work with it in this manner, okay, so we are going to have our cell value of, okay, 0, our cell number is 0, 1, 3, 2. We are going to have 4, 5, 7, 6. Okay, so let's see. We're going to have 4, 5, 7, 6. And let me see. Okay, so we have a 0 here to be for a 0. We have a 1 here for 1. So we have 6 here. So 1. We have 7. We still times the 1. Okay. So let's work with this and see. So let's work with this and see. Okay, so the corresponding, this is 0, you flip it, you get C prime. So up here you have 0 and 0. You get an A prime, right? 0 and 1, we don't consider. So here becomes a 1, so you have a C. 1 and a 1 retains you an A. Gives you an A, right? So please, if I get you right, this was the final expression that you derived.
Yes.
Okay. So we derived, so if you use the other way I believe you derive an expression of please, what was the expression that we had?
A prime B prime
Yeah.
plus
A prime B prime plus AB. Right.
Yes,
Plus
exactly.
AB. So let's test if these two expression has the same return value. Okay. So let's conduct a simple test. So let's take three sets of inputs where we have C being 0, A being 0, and A being 0. So 0, 0, 0, right? So if C is 0, A is 0, B is 0, so C prime becomes 0 prime, we have 1, right? Times A prime is also 0, we have 1, right? Plus we have C prime, we have C is 0, and then A is also 0. So we have 1 and 1 returns a 1, right? As the first output. So the first output for the first problem is 1, or for the first F value for the this K-map is 1, and for our other K-map is also for this K-map is 1. Let's look at the other. We have A being 0, so A prime is 1, B prime is also 1, right? Plus A is 0, B is 0. So we have the same thing here. So 1 and 1, we come up with 1 as well. So we also have our return value being a 1 and a 1. So I'll say that this agrees, okay. So now let's look at another set of inputs and see. So we have 0, 0, 1, okay, where A is 0, B is 0, and C is 1. So if A is 0, here becomes, and C is 1, so C is 1. So if you flip it, you have 0. This is 0. B is 0, doesn't apply. C is 1, we've already applied. A is 0, so that becomes a 1. 1 times a 0 plus, let me see, a C, our C is 1, A is 0. So this still returns a 0, you have a return value 0. Then you have A prime, B prime, let me see, so A prime, B prime, you have 0 prime, 0, but that's 1 by B prime, 1, 1 here, then plus 1, 0 there. Here returns a 1, it does not tally. So I cannot guarantee, okay, honestly, I've not thought of drawing it this way. I cannot guarantee. But I know the correct answer is A prime, B prime, AB. That's the method that I've always used. But so do you know something? We have another session on Friday. So what I'm going to do is that I'm going to compare the two methods of drawing K-map properly. Okay, if we were to use maybe a 4x2 K-map, I can guarantee that the result is going to be the same. But as in using a 2x4 K-maps and then swapping the position of the inputs, I cannot guarantee if their outputs are the same or if they are the same. But then I'll check. But somehow I believe that these two equations will technically have to be equal, because this way of drawing it is technically not wrong either, because I believe that the cells are represented correct. But let me explore that, and then in our next session on Friday, I'll properly clarify that, okay. But please, for now, let's go with representing our first input A here, and then our next two inputs B, C right here. Okay.
All right. Please,
Okay, so
my next question. My network was not really good, so I didn't get the don't care. The don't care value, I didn't get that one really well. So if we can take that one again. How do we get the don't care value?
Okay, so I was
What is the don't
explaining
care
that.
value? I didn't get that aspect well.
All right, so I was explaining that when it comes to our cells that are don't care or that are specified to hold don't care values. In this case, we have D into bracket 3 and 5. That part particularly means that those cells can hold values of either 1 or 0, okay, dependent on the kind of problem you are dealing with. If you are dealing with a problem which involves mean term values, those cells takes 1. If you are dealing with max terms, okay, so mean terms, that is with sum of product expression, okay, then that one, those cells are going to take 1. So for instance, you have 3 and 5 to be your don't care. So 3, this takes 1, 5 takes a 1, okay. So in a case where you are dealing with a max term function instead, which is a POS, a product of sum expression, then those cells take a 0 and 0 instead, okay. So those cells are sometimes deemed negligible as the name goes, okay. They can sometimes be, or they can be neglected at times, and then it does not impact the final output of our expression, okay. But I'm going to show you in other scenarios, especially when you are working with 4x4 key maps, where sometimes your don't cares are actually very, very important for you to obtain the final output. But in this scenario where you're able to get your 2 adjacent cells here, your 2 adjacent cells here, technically the don't care cells will rather complicate your expression and might need a further simplification, okay. So that was the explanation I gave for the don't care. So in this scenario, we decided to ignore our don't care values since they technically do not really affect the outcome of our final expression. Okay.
All right, thank you.
Sure. So I have a lot more problems here that I might want us to look like, but to look at, but the time is far gone. There are different scenarios. There are times you'll not be given anything, don't care. That one is much simpler and straightforward to work with. There are times that you'll be given actual expressions instead of giving you the mean terms. If they give you this, I see it as it is easier and direct to work with. If you are giving the raw expressions, okay, we also have a way you approach it. There are different ways in which questions will be given. But since we've been able to do majority of what I'm supposed to do now, I think at our next meeting, we are going to look at other minor concepts and that came up that we couldn't explore today. And then we are going to use the rest of the sessions to solve problems and then questions and K-maps. Okay. So please, if no one has any question, for the sake of time, we might have to end our session here. Please, does anyone has any question, contribution, or anything to say? All right, if none, then we'll call a closure to the meeting, please. So please, I'm going to meet you again on Fridays.